Hello everyone. Thank you for coming this graduate talk. Jiayin today will give a presentation about joint multi-dimensional resource slicing and scheduling. So thank you very much for coming this graduate talk. So Jiayin, you can start if you want.
Okay, thank you. Good morning. I'm Jiayin Chen, and I supervised by Professor Shen. And today I will give my presentation about the joint multidimensional resource slicing and scheduling for safety message transmissions in vehicular networks. And here in the title, the multidimensional means the multidimensional resource refers to the wireless communication resources and the vehicular sensing resources. And for today's talk, I will follow this outline. First, I will introduce the safety-related message transmission services and the edge-assisted vehicular networks. And after that, I will talk about our proposed joint resource slicing and the scheduling scheme and show some simulation results. The automated vehicles are equipped with the in-vehicle sensors, as we can see in the figure. It enables the vehicle observing the surroundings and making decisions on driving. But if we only rely on the in-vehicle sensors, it will limit the view of an automated vehicle. For example, the vehicle cannot see what is happening around the corner because of the line of sight constraint, and it is also limited by the sensing range. And to improve the autonomous driving performance, the communication technology are applied for this. It includes the vehicle-to-vehicle connections and the vehicle-to infrastructure connections. And this type of vehicles that with the connection technology, we called it the the connected and autonomous vehicles. Oh, sorry. Oh, sorry, there's something wrong with the slides. And okay, I continue it here. And this, okay, here to improve the autonomous driving performance, the communication technologies are applied for the automated vehicles, and this technology can enable the connections among vehicles and between vehicles and infrastructures. And this type of vehicles is named as the connected and automated vehicles. And this cooperation can help to improve the driving safety. For example, if the vehicles can share the sensing data with its neighboring vehicles, and this can provide a comprehensive view of the environment and overcome this constraint of line of sight and the limited sensing range. And another application is the cooperative localization. That shows a more accurate localization performance for all the vehicles. And in addition, this connection can also help to improve the optional efficiency. Like if the vehicles can share their trajectory information and they can make a better trajectory design decisions. And to enhance the road safety, some message transmission services are proposed to enable the information sharing among the vehicles. First, we talk about the cooperative awareness messages called the CAM. They are required to be exchanged periodically among the connected vehicles to deliver the vehicular moving status, including the vehicle ID, the position, and their speed. And secondly, if there are some accident happens, the decentralized environmental notification message called the DENM are generated and transmitted to report this accident. And this can help to avoid the further road risk. So the transmission of DENM is event-driven. And as we mentioned before, the automated vehicles have the capability of sensing the surroundings. And so this object may be the non-connected road users and some safety critical objects. And to further empower the road intelligence, the collective perception service has been proposed. Enabled by the communication technologies, the vehicles can generate, send, and receive the CP message. Here we call it the CPM to exchange the sensed environmental information. And according to the integration of CPM, the perception range can be extended and the accuracy is improved at the same time. Next, I will introduce the Edge Assisted Vehicular Network. Here we consider an urban vehicular network. As shown in the figure, the RSU is deployed at the intersection, and this RSU can support the message relay and make resource allocation decisions. And the coverage of this RSU is divided into square blocks, and the set length of each block is set as the way-to-way communication range. And this guarantees that there are no way-to-way connection among any two blocks with the same color as shown in this figure. And the vehicular network includes two types of connected vehicles. One is the sensing-enabled vehicle called the SCV in this work, and the other one is without the sensors called the UCV. The SCV can detect the objects in its sensing range and also generate the sensing report periodically. And the transmission of message are supported by the way-to-way connections. However, due to the limited height of the vehicles, the link connection may be blocked by some like trucks, buses, or the buildings. So to deal with this problem, the way-to-way connection is enabled between this RSU and the vehicles. And we consider the half-duplex feature of the connected vehicles. So these vehicles cannot receive and transmit packet at the same time. So here we consider the way-to-way connections between one sending vehicle and its targeting receivers, and to guarantee the different vehicle groups in the different colors as shown in this figure. Next, I will introduce the wireless resources that can be applied for message transmissions. As shown here in this figure, the wireless resource pool is divided into resource blocks, and each RB represents the usage of 200 kHz bandwidth for 1 millisecond. And the wireless resource allocation is implemented through allocating this RBs to the vehicles for their message transmission. And to avoid the interference among vehicles transmitting message, we allocate the different subframes for way-to-way uplink and way-to-way transmissions. And then for the vehicles receiving the message, we split the frequency band for the downlink transmission and the way-to-way transmission. As in the figure, we show it as this red line. And here, an example is given in the figure for the resource allocation result for the vehicles in one group. And from this figure, we can find out the way-to-way mode vehicles are allocated with the different subframes as the orange blocks in this figure. And the unoccupied subframes can be utilized by the other vehicles in this group for their way-to-way uplink transmission, shown by this purple blocks. And we can find out that in one subframe, the multiple way-to-way mode vehicles can use the different RBs to send their messages. And for way-to-way uplink scheduling, the RSU receives the packets from all the vehicles in its coverage. So for the uplink collection may happen among the different groups with the same time segment. So when making this decision for the uplink RB, the vehicles in these groups should be considered together. And this means the uplink RB allocated to the vehicles from these different groups should not be overlapped, as these purple blocks given in this figure. And for the way-to-way downlink, after the RSU receives the packets, the downlink RB should be allocated to transmit the packets, and the downlink resource pool consists of these unoccupied RBs beyond this red line given here in the figure. And this downlink resource pool is shared by all the way-to-way mode vehicles under this RSU. And next, I will talk about our proposed joint resource slicing and scheduling scheme. This scheme is we call it a GRSS scheme. And in this work, our objective is to minimize the delay and maximize the successful reception rate for DNM and CM transmission. Well, for the CP services, we aim at optimizing its overall sensing quality. And so we propose a GRSS framework to make the resource allocation decision. This framework, including the offline optimization stage and the online decision-making stage. As you can see in the figure, this is the offline optimization and the online decision. First, I will briefly introduce the offline stage. It is this multidimensional resource allocation scheme called this MRA scheme is designed to optimize the resource allocation based on the historical network information. And here, the information includes the vehicle's mobility, like the vehicle ID, location, and speed, and also the vehicle's sensing capability and their transmission request. And the output decision includes the selected vehicles that will generate the CPM to support the CP service and the selection of the transmission mode, like the way-to-way mode or way-to-I mode, and also the RB allocation result. And for the online decision-making stage, to adapt to the real-time network conditions, we design a learning-based resource slicing and scheduling scheme called the LRSS scheme to make these online decisions. And we propose a collaborative scheme between the resource slicing and the scheduling, as here in this figure. This is the resource slicing module, and this is the scheduling module. And in our work, one slice is built for the vehicles in each street block. And here in this figure, this red block is showing the one vehicle group. And considering the relationship between the numbers of allocated RBs and the number of requests, we can apply the resource slicing technology to enable a parallel decision making for the different groups and the different services. And here, this learning-based slicing module is trained based on the wireless resource allocation result achieved by the MRA scheme, which is the offline optimization scheme. And then with this resource slicing result, the RB are allocated to each vehicle by this resource scheduling module, including the decision for both slicing resource and the wireless resource. So next, I will introduce more details about this two stage. First is for the offline optimization stage, the MRA scheme. And in this work, at the beginning of each CAM period, the vehicle needs to send its request to the RSU for DNM or CAM transmission. And the RSU determines the transmission mode and allocate the RVs to support this request, to support their request. But for the CPM transmission, the resource allocation decision is made for the both sensing and the wireless resources, including the selection of the CPCD vehicles and the RB scheduling. Here we consider the different message priorities. So the RSU first allocate the resources for the DNM and the CM transmission, like given in this figure. And then is for the CPM transmission. And since the RB available for the V2I downlink transmission can only be determined based on the uplink resource scheduling result. So here the last step is the V2I downlink RB scheduling. And to select the transmission mode for the vehicles, we need to consider the resource consumption for these two different transmission modes. And if a V2I mode is selected for a message transmission, it means both uplink and downlink resources are required, which is the double of the resources required by the V2A mode. So to improve the resource utilization, the V2I mode is selected only when the V2A mode cannot satisfy the transmission requirements. And here we have two motivations of selecting the V2I transmission. The first one is the subframe insufficiency. If all the vehicles transmit message with V2A mode, so the least possible number of required subframes is equal to the overall number of the requests. So when there are more requests than the subframes, it means the subframes are insufficient for this V2A mode. But as we discussed before, the one subframe under the V2I mode can transmission or multiple messages. So this problem can be solved through selecting the V2I mode for this request. And another motivation is the non-log set condition. If the V2A link is blocked and the message should be relayed by the RSU to improve the transmission reliability. So it means the message is transmitted through the V2I links. And the RSU allocate the wireless resources for the received DNM and the CM request. And here the DNM always has a higher priority. And based on the location of a vehicle, the RSU can obtain its target receiver set, which consists of the vehicles within a relevant distance. And considering the possible non-log set conditions for the V2A connection, the feasible receiver set here is a subset of the target receiver set, and the gap between these two sets is the potential message loss if we're selecting the V2A mode for this message. And this is also defined as the potential gain of selecting the V2I mode for the vehicle. So the vehicle with a larger V2I gain has a higher priority to use the V2I resources. And after the resource allocation for this DNM and CM, and we consider the CPM transmissions. And the number of supported CPM upload transmissions for each vehicle group can be obtained. And this will be used as the resource constraint in the following steps. And to support the CP service, in addition to this wireless resources, we also consider the sensing resources. And here we select the SCV as the CPC vehicles to improve the overall sensing quality. And first, we consider the sensing range of each SCV as shown in this figure. And if one object is sensed by more than one vehicle, the sensing error is measured by the vehicle nearest to the object. So the gain of selecting one SCV as sensing vehicle is defined as the decrement of the overall sensing error achieved by this SCV. And we will greatly select the vehicles with the highest sensing gain to generate their CPM. And then I will introduce the more details about the online stage, this LRSS scheme. In the MRI scheme, the decision on the V2I mode selection is made iteratively for all the vehicles, which requires a large number of iterations, especially during the high traffic hours. There are a large number of vehicles on the street. So to improve the time efficiency, we design a slicing module to estimate the number of V2I uplink RBs allocated for the transmissions. And this can decouple the V2I mode selection among different groups and different services. Here in this figure, the result slicing module consists of 3 functions, and 2 is about the slice formation, and 1 is about determine the uplink RB slicing result. And based on this result slicing result, the RB scheduling function determines the vehicles that will providing their sensing data and allocate the RB for each transmission request. And comparing with the sequential decision making in the MRI scheme, this slicing-based RB scheduling decision can be made in parallel for different vehicle groups. And in each vehicle group, the vehicle with the higher V2I gain are allocated with the V2I RB and held the RB as used up. And in this online stage, for each established slice, the slice parameter estimation function is used to determine the amount of allocated resources based on the information of vehicle's request. And to estimate this V2I uplink RB demand, we need to model the mapping relationship between the request and the allocated resources. And here, without a mathematical model, we apply a learning-based method, the backpropagation network. Due to its multi-layer structure, the BP network can mimic the complex nonlinear mapping relationship. And if we have some unexpected input, this error backpropagation can help to adjust the weight and to minimize the estimation error. And as we given in this figure, a BP network is trained for each vehicle group, and the network consists of the input layer, 2 hidden layers, and the output layer. Here, the numbers of received DNM and CM requests are utilized as the input, and the output here is the allocated V2I uplink RBs. And to train this learning module, we run the offline optimization scheme, the MRI scheme, and record its V2I resource allocation result to obtain this training data set. Next, we simulate the proposed resource allocation scheme and evaluate the performance for message transmissions with these allocated resources. In our simulation scenario, one RSU is deployed at the intersection and the vehicles driving through its coverage area. And we assume all the vehicles have the capability of sensing and communication, and the sensors are configured following this table. And the CM transmissions are requested by all the vehicles, while the DNM requests are rest randomly. And here we also consider the different performance metrics for the different type of message. To show the adaptiveness of the proposed scheme to the vehicle density and the DNM service request, we evaluated the performance during the low traffic area hours and during the high traffic hours. And we also changed the probability of DNM requests. And here for the transmission, the reliability is evaluated as the proportion of the successful receptions. And as we can find in these figures, if we only rely on the way-to-way connections, as the first two blue bars given in the figure, nearly 96% of packets are successfully received during these low traffic hours. But if we consider the way-to-way connections provided by the RSU, we can achieve a nearly 100% successful reception. Well, for the average delay of message transmission, we evaluate the simulation results are given in these two figures. The average delay keeps lower than 1.5 millisecond and 8.5 millisecond for the low and high traffic density, and this can satisfy the requirement of safety-related applications. Well, for the CP service, both the coverage and the accuracy of sensing are evaluated. In this top figure, the CP coverage refers to the proportion of sensed blocks in the street area, and it shows the coverage rate is determined by the density of the vehicles. So with more vehicles on the street, we can achieve a higher coverage rate. And the sensing error is also evaluated. Here in the bottom figure, the CP error refers to the average value of all the blocks, and with a lower density of vehicles and a higher probability of DNM, it leads to a larger average CP error. And to compare the time complexity of the MRA and LRSS scheme, we evaluate their running time with the changing numbers of the DNM and the CM requests. And in this figure, an almost linear increasing trend is observed for the MRA scheme. But for the LRSS scheme, we can see that the running time is almost not changed. And this result proves the low complexity of the proposed GNSS framework in the large-scale vehicular networks. Next, I will summarize this presentation. A joint resource slicing and scheduling framework is proposed to support the safety-related message transmission in urban vehicular networks. And both wireless and sensing resources are allocated for the vehicles with the request of different with the request of different transmissions. And the service requirements are considered for each message type, and the scheme is also customized to satisfy their service request and to optimize their QoS metrics. And based on this time complexity evaluation, we can prove that the proposed GNSS framework can make real-time decisions and can apply into a large-scale vehicular network. Okay, thank you for your attention.
Thank you, Jiayin. Thank you for your presentation. So, any question from our attendees? Yes.
Yes. Hi, Jen. This is Kong Hao.
Hi.
I have a question because the presentation is related to the safety related message transmission and about the reliability. So maybe I missed something. Could you introduce some details about your performance metrics about the reliability? Because in your simulation, I see some like about the sensing error and reception, something like that. So could you give me some detail about the reliability?
Okay. For the reliability, maybe I will turn to the page of the simulation result.
That's
Here.
Yeah.
Yeah. The reliability is in our work it means the successful reception of the packet. It's like the transmitted packet can be successfully received by its target receivers. So I think this is how we evaluate the reliability in this simulation.
So how does the successful reception is your objective or a constraint?
It's not a constraint. We want to maximize this successful reception. So yeah.
So okay, maximize okay, I see. So how about the sensing area in maybe the next page or next?
Yeah, the sensing error. Yeah, the
Is
sensing error is we consider the two metrics. The one is the coverage. Coverage means that the street is sensed by the vehicles, and so the coverage rate is the proportion of the sensed blocks to the whole street area. And another metric is the sensing error. Here is the since for each sensing vehicle, it's the sensing error of the object is related to the distance between the object and the vehicle. And so for each vehicle, it has a map about its sensing error in its sensing range. And here this sensing error is we consider the integration of all the CP message generated by the vehicles. And for the integrated message, we evaluate this sensing error. We call it the CP error in the figure.
So the sensing error you considered in this problem is like a aggregation number or for aggregation value for all users in the coverage.
Yeah.
Okay. And I see. How does this the sensing error impact the successful reception ratio? Or there is not a relation between these two things.
Yeah. The reliability here. For the different types of message, we consider the different metrics. So the reliability, as you mentioned, is for the DNM and CM transmission. So for the CPM transmission, we consider the sensing performance, like the accuracy and the coverage rate. So they are not for the same type message. So we not consider them together.
Oh, I see. Thank you so much. Yeah, I get it.
I have a small question. I may be missing something, but I was wondering. So you consider both planning and scheduling. So how you planning policy changing according to the scheduling maps? So different scheduling policy will result in different planning results, I think.
Yeah. So you mean how
they are joined
scheduling?
together?
Since in our work we have this offline optimization scheme, and so this is not split by the slicing step and the scheduling step. This is like one algorithm that to make the resource allocation decision. And based on this scheme, we design this slicing and scheduling modules. So in our work, the resource scheduling module is designed based on the MI scheme, our offline optimization scheme. And so I think we don't consider the different resource scheduling scheme here. We follow this.
Just I have a question on the figure. So basically, you have the QoS report and return the scheduling module. There's a QoS measurement. So the QoS measurement will report to the slicing module. It's like the feedback. So yeah. So the scheduling normal in the really small time scale, like a millisecond. However, the slicing module, so the slicing module will receive like the aggregated measurement and do the adjustment. Or so it's like if the QoS is bad, so it will trigger the slicing, or it have a fixed time window, and see what happened in past time window to adjust according to the reported QoS and adjust the slicing policy.
Oh yeah. I think I understand your question. So it's about how we update this resource slicing result, just how to trigger this slicing.
Yes.
Right. So, in our work we don't have a time window for the resource slicing, but we consider this QoS measurement. Yeah, this we use this feedback from the scheduling module to trigger this slicing. When we need to update the slicing.
Oh, okay. I got that. Thank you. Any question from our audience? If no questions, so thank you very much for attending this seminar. So we have an evaluation form, and the link is already attached in the chart of this window, and also you can find that on the email. We do the announcement. So thank you very much. So thank you, Jiayin, for your presentation. So we can stop right here.
Okay, thank you.